So it's day 2, but we've got a couple of minutes before the problem opens up, so I figured I would cover a refactor that I made to day 1 very quickly. There were some questions in the comments about how do you ensure that a non-parser has consumed all of the input. There are basically two options. One of them is using all consuming on your parser, which will make sure that all of the input has been processed for you, or in the return type here, that will be the rest of the input, and you can always check to see if this is empty with something like input dot is empty. So what I did here is I created a dial that represented the actual sort of padlock that we were swinging back and forth. This has a default implementation, so this is a struct with a location that the dial is currently pointing at and a number of revolutions, or the number of times we've seen 0. The default is the default from the problem, so pointing at number 50. 0 revolutions to start with. I moved the spin function into that structs impl so that we can go up here and for every direction just run dial.spin, which mutates this dial, and at the end we just get the number of revolutions. So I'm reasonably happy with this in terms of solution. Most of the logic for how to deal with spinning is now in this spin function, which can be tested separately. I also added a add impl for direction for i32 so that you can add a direction which comes into the spin function here as rot, and we can add that directly to the i32 without doing .0 or whatever like that, which is really nice. And then we just update the state. So this is a mutable reference to self or an exclusive reference to self, which means that every time we run dial.spin, we are mutating the values inside of this dial. I also cleaned up the non-parsing a little bit. I like to use preceded. So instead of splitting this out into a separate match, we're doing an alternate between a parser that accepts L and then an I32 and a parser that accepts an R and then an I32. An interesting note about enums, if you aren't aware of them in Rust, is that they also basically create a function that can construct that direction or that enum variant. So in this case, we have an enum up here that is left and right that contains a number. These can both be treated as functions of one argument. So in this case, we're doing a non-parser that looks for L and then parses an I32 and then puts that number inside of direction left. And the same thing here, looks for R, parses an I32, and then puts that inside of direction right. So we don't need to do any additional matching, no more additional panicking, anything like that. So this is up on GitHub if you want to see it. And I believe we should be at time. Yeah, so we're within a minute for day 2. So let's get started. The first thing I'm going to do is run my just create day 2, which should work, provided day 1 worked yesterday. And we are all set up and ready to go. So day 2 is gift shop. You get inside, take the elevator to its only other stop, the gift shop. You aren't even sure who's allowed to visit the North Pole, but you know you can access the lobby through here. And from there, you can access the rest of the North Pole base. There's an extensive selection. A clerk recognizes us. An elf added a bunch of invalid product IDs to the database, so we're identifying invalid IDs in some way. They only have a few product ID ranges, the puzzle input that we'll need to check. For example, it looks like this. So this is going to be our test input to start with. I think this is one line. Sometimes it's hard to tell. It looks like multiple lines, actually. We'll just do a quick zoom out, zoom in. Maybe I'll check the actual input before we actually get started to make sure that this is supposed to be multiple lines. But miscopying input or something like that is a rough spot to spend too much time on. So the ID ranges are wrapped here for legibility. In your input, they appear on a single long line. So we only have one line. So let's get, that is really unfortunate in terms of setup, but it's supposed to be one line. And I'm glad they put this comment here. The ranges are separated by commas. Each range gives its first ID and last ID separated by a dash. So this is basically like a range inclusive, is what I'm thinking. Rust has a couple of range types. Since the young elf was just doing silly patterns, you can find the invalid IDs by looking for any ID which is made only of some sequence of digits repeated twice. So 55, 5 twice, 64, 64 twice, would all be invalid. So these are product ranges, and we kind of need to iterate through them to find all of those. Which is interesting. Okay. None of the numbers have leading zeros. 0101 isn't an ID at all. 101 is a valid ID that you would ignore. Find all of the invalid IDs that appear in the given ranges. So this has 11 and 22, which are at the ends. So this is an inclusive range for sure. 95 and 115 has one invalid ID, 99. Is this only twice? Some sequence of digits repeated twice. So my question here is, does it need to fill out the entire number, or can it be, I guess it has to fill out the entire number is the assumption that I'm going to go with. So we are going to get basically a range of integers. We are going to want to split it in half. All of these look like they are even. I'm assuming that's intentional at the moment. And then we basically compare first to last, or rather first part to second part. And if they are equal, then we have an invalid ID. And naively, we can just go through all of the numbers and check them all and count up the invalid IDs. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.2 billion IDs are invalid. So we might need to be a little bit smarter in how we check that. And the thing that comes to mind is basically nothing that sounds accurate. I'm not sure how we're going to cut this down. I guess we can start by not cutting it down because we never really know. What part 2 is going to bring. So I think we'll do it naively to start. We need to be able to keep a billion numbers. This can at least be parallelized, so all of the ranges can be operated on independently. So we'll just rush into this and do it naively and see what part 2 has to say about it. Because optimizing a solution ahead of time for part 1 is almost always a mistake. So we have a test with all this input, and this is supposed to be this number, which is quite a large number. Now, if you're using Rust and you're not used to numeric types, you can always find what the maximum for a particular type is. So in this case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 4 billion, which is less or more than we need to store this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a fourth of the space that we have. The numbers themselves don't look like they ever reach above that. We could turn this into a U64 if we needed to. I think that changing from U32 to U64 is not terribly important. 3, 4, 5, 6, 7, 8, 9, 10. It does look like we might need to, though. So, for example, this is 10 digits and it starts with a 6. So we do actually have to use U64 at least. And I think one of the interesting things here is actually that I'm noticing there's a lot of prefixes that are similar. So for example, in this first input, it's 3335, and this is also 3335. That means we really only have to test 10 numbers to see if they're in that range or not, because it'll be 3335, and then if this number wasn't here, it would be like 0 through 9, right? And then it would also have to be 3335, 0 through 9. So that brings us to something along the lines of if there's a prefix that matches, then we can greatly cut down the number. But let's start naively and get our answer and see what part 2 has to say about it. Even if this is too slow, we will be able to see how slow it is and then improve from there. So I'll start off with ranges. I think what we're going to end up here with is going to be a vec of inclusive ranges. One of the really nice things that I haven't talked about yet is using to do here means that this function that we don't have anything returned from yet is causing a compile error, right? So if we do a cargo test p day 1 part 1, sorry, day 2 part 1, I don't know why I said day 1 part 1. Day 2 part 1 will fail to compile mismatched types. We're not returning a result here. So if we want to temporarily prevent that from stopping us from working on our program, we can use the to-do macro. And it accepts a message here. It's only going to be temporary for me. I'm not going to commit it or anything, so I'm not going to leave a message, but it accepts a message. So this is basically going to be separated list 1, where the separator is a comma. And I think we have separated pair, where this will be like complete. I think we have complete U64, followed by a tag with a dash, followed by a complete U64. And then this will parse the input, and we will end up with tuples here. of U64s, and I'm going to want to map this into probably a range. So we'll call this start and end, and I'm just going to say start dot dot equal end, I think. And I think this comes in as a tuple, actually, not as two arguments, which brings an interesting question as to why this is. So basically what this is saying is it can't figure out what the error type is supposed to be for the separated pair. If we look at the type signature here, we can see quite a few generics. So because this parser basically accepts three parsers as arguments, we end up with the input type, the two output types for the first parser and the second parser, and then the error type. And then F, G, and H are the types of the parsers, which are also generics. So there's a lot of generics going on here, which can be a little bit scary if you're not used to them. So especially when you're starting, probably the easiest way to fix something like this and to get through kind of all those generics and give some concrete types to things is to just split that out into a separate parser like this. However, once you do that, you may be able to see the mistake that you were making, such as, for example, this semicolon. Because of that semicolon and that to do, the type inference wasn't coming through from the return value to where we were using it. So that error type didn't propagate through the type system. And that's all that was happening there at the end of the day. This complete U64 needs to know what the error type from this iResult is, because all of these parsers need to use the same error type, which is not strictly speaking true, but for this example, we'll say that they need to share the same error type. Thus, the error type comes from this result, right? This is a result of a tuple and an error. This error type is the one that needs to propagate. If we are returning this value, then that error can influence the chain of parsers that we have here. If we don't return it, right? If we have this semicolon and we have this to do, then where is that information supposed to come from, right? We're not actually returning the value, so it can't get the error from this type and pass it into what should be happening here. So just a quick kind of like aside for debugging things like this, splitting things out into multiple pieces can make it more obvious as to what is actually going wrong, which isn't always some type puzzle that you need to solve. Now, one of the other things that was asked about in the comments that I covered at the beginning of the video is this non-combinator all-consuming. This will make sure that this ranges parser actually consumes all of the input for us. It just does that by checking to see if the input is of length 0. If you click into the nom library and you look at some of the internals, you can see that input length equals 0 is what this is checking for. And I'm using Miet as my error handler here. So I have a couple of options. In this case, I'm just going to return this string here, failed to parse AOC input. This should never really happen unless I wrote something wrong. So we should have our ID ranges now. So now we should have our ID ranges. We'll want to iterate over them. We can actually get the start and end values back out of this range inclusive if we want them. And from here, we can probably start with something that's pretty naive. So this will be a loop. So this technically works, but I'm a little concerned. Adding up all the invalid IDs. Okay. That's the part that I missed. I thought we were going to count up a billion IDs, not that we were going to add up all of the invalid IDs themselves. That's significantly different. I'm much less worried about performance at this point. So we have a U64. We need to basically split that into 2 byte slices or 2 somethings, 2 slices of some kind. We could to string this and then work on each slice of strings. And half for us, because we're using U64s, is always going to be 4. And this is a U32 instead of a U size. Is that the issue? Yeah, cannot index into a value of type U64. That's because I didn't use the right variable name here. And if I change this to be id stir.length over 2, then we end up with the right half, which is not 4 because we don't have a U64 anymore. We have a string slice. I'm doing my math terribly today. But we end up with all of these numbers, 11, 22, 99, 10, 10. All these numbers are the right numbers. So we can just have an accumulator, start off with 0. And if they are equal, then total plus equals ID, which doesn't have mute on it. So we'll do mute here. And of course, I am still returning nothing because I have this to do. So we need to do a return of total and just to string it, because all of my results are supposed to be that. And then we passed our test. So let's go for day 2, part 1, and find out that I have a new line at the end of my code, which I feel like is fairly common. So we could update our parser to be resilient to that, or I could just delete the new lines and we could move on with our advent of code process. So hopefully this is the answer. This is the answer. 1 gold star. Perfect. So I was trying to be a little bit too smart. I messed up my math a couple of times. We have a total here. We have a set of ID ranges, which are range inclusives. That's the key point here, a range inclusive, which is dot dot equals. So let's start dot dot equals end, which includes the first and last numbers in this range. We iterate over all of the ranges that we parsed. We iterate over the ranges themselves. So this is each number. I realize I named all of these variables ID something or other, which is not the best. But I'll come back later and refactor this basically. We take these numbers, these U64s, and we turn them into strings, which we can then get half the size of, which in the real world, we could end up in a situation where this half is not half of the actual string slice. For advent of code, this is a property that is guaranteed by the input. So if we take the half and we use these half ranges, so everything from beginning to half, and then everything from half to end, in this string slice, if those two slices are the same, so we're not copying anything here, we're not cloning the string again, we're just comparing the two slices to each other. If that is true, then we add that to our total and we move on. So the clerk quickly discovers that there are still invalid IDs in the ranges in your list. So now an ID is invalid if it is made only of some sequence of digits repeated at least twice. So I guess 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 3 times, 1, 2, 1, 2, 1, 2, 5 times, 1, 7 times are all invalid IDs. So the question is, how do we now determine these variable sized potential ranges? So each one ends up having more checks to do, basically. So my naive thought, we're adding them all back up again. So this is the original example again, right? This is not a changed example. This is a different example, isn't it? From the same example as before. I think that's this one. So I think we're good. This is describing the example that we're using in our test currently. So let's grab this code. Let's dump it into 2. And then the output is actually going to be this number. It's good that we're using U64s here, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because this gets pretty close to U32 max. So here we do another loop inside of this is basically the answer. And the question is, how do we want to deal with these expanding ranges? So I think half is still relevant because half is the max that we can be repeating on. We can either repeat on 1 dot dot half sizes of characters, right? So if we have 4, half is 2, then our index will be either just 0 or 0 and 1 needs to be repeated. Because 0, 1, 2 can never, like a 3, if we have 1, 2, 3, 4, or something like that, right? And we're tracking for 3 numbers, this can never repeat because there's not enough values left. So we only need to process up to halfway through the number. We are using ASCII, so we can do this kind of math on string slices right now. We're pretty much guaranteed to not have any, alternate characters or things that would place us in the middle of an emoji or something like that. So I think for 0 dot dot half. So for limit and 0 dot dot half, this gives us all the individual numbers for the number of, or the size of our slices, we should say. I guess the other thing that we could do is find all of the common divisors, if you will. So if we have a number that is, let's say, 8 in length, right? We could have a duplicate that is 1, 2, 3 wouldn't work, but 4 would, right? And these are all the common divisors of 8. So realistically, we could trim this down even more. I don't think we have numbers that are that big that we really need to care. If we look at the input, we're looking at numbers that are like at most 10 digits in length. So we will at most kind of have a 10 digit number. which will be 1, 2, 5. So we would cut out 3 and 4, which I'm not sure is really actually worth the extra processing, but we could definitely limit it more if we wanted to. So we've got our ID string, and we've got the current limit that we need to be processing. And this check needs to come in. So it'll be slightly different. So this is not exactly the code that we're going to have. I guess we can do that check here if we wanted to. We could do IDStir.length, I think rem Euclid limit plus 1. Let's run our part 2 here instead of our part 1. So you can see that we're getting mostly zeros, which is pretty much expected because 1 character and 2 characters fits a lot of these because they're all basically going to be even anyway. So whenever this is 0, we have an opportunity. So if this is 0, then we can info this log. And in my test, I will do test log test so that we can get some of this output since we are, I'm running it actually, I'm not testing it. Just make sure our logs are working here. Running 0 tests. Why is this running 0 tests? Did I mess something up horribly? Hold on. Day 2, part 2. Day 2, part 2. Day 2, part 1. This is still tests. Got my module. In this case, I've got test log test, which should be fine. It doesn't work on either of them, though. Oh, because I'm running bin. That's why. So what I had here is I was doing cargo test for a package of day 2, but also the bin part 2, which means that it was only picking up tests for the part 2 bin, which doesn't include the tests for part 2. So here we go. We're good. I'll throw a skip input in here so that we don't get that extra input. And it looks like we get limit 0, so the first character, limit 1, 2 characters. This is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5. So 1, 2, and 5 are the possibilities for this. Same for any number like that. So technically speaking, we don't actually need to continue doing this math over and over. We have a bunch of numbers. We know that they are 10 digits or less. We could store some kind of map instead of doing this over and over. I'm not terribly worried about it though. So if we could have something that is a multiple, how do we actually check? So in slices, there is a function called chunks, and chunks will give us an iterator over chunk size elements of the slice at a time. This is in contrast to Windows. The example here is lorem. So if we do chunks2, that'll be LORE and then M. We've already done the math to determine that this is going to be a multiple. Unfortunately, we don't actually have like a slice in the sense that this is expecting. We have a string slice. So if we set the prefix to the ID string slice from 0 to limit, we could do .enumerate.cycle here, right? So cars enumerate cycle zip ID dot cars AB. I guess we don't need enumerate here. If we just cycle over that subslice of characters, we zip it with the original characters, then we should be able to do, I think, AB, which accepts a tuple. We don't need the into iter. I was mistaken. A equals B. So if this is true, right, if we take that subslice of the string slice, we take those characters, we cycle them in an iterator so they repeat over and over, and we zip those together with the other cars, then all of them should match, right? Because we have a repeating cycle of these characters, the multiple is the same, and if they all match, so let all match, and then if all match, then total plus equals ID, and then we're going to continue outside of this because we don't want to add it twice, right? So if we test this, our test now passes. So I do feel like I can clean this up a little bit. Maybe we'll do a refactoring later. But basically what we're doing here is iterating over all of the ranges for all the IDs. For every number in each of those ranges, we are turning that number into a string slice, or we're turning it into a string, sorry, not a string slice. We are getting half of the size of that string slice, and we're iterating over a number from 0 to half of the size of that string slice. If the number that we are iterating is a multiple of the total length, then we have a potential match. If we take the string slice from that string and we cycle those characters in an iterator, which is an infinite iterator, We zip that with the characters, which will truncate this to only the size of the length of the ID string. Then all of those, which ends up being a character from each of those iterators, they all need to match. And if they all match, then we add to our total and continue. So if we run part 2, we end up with this massive number, which is not the right answer and is too high. Perfect. So let's make a note of that. Nope. Let's make a note of that. Too high. Why is it too high? This number seems excessive. There's something I missed in the input. Our test is passing, which is not good. Right? Day 2. Oh no, our test is failing. I ran the wrong command. Okay. That's good to know. At least our test is failing. We have too many. Why do we have too many? Because it's not continuous break, which still gives us a number that's way too big, which is interesting. So let's print out all of the numbers, right? These are all the numbers. Let's print these out. We now have the list. This is too many, way too many. So I think we need a special case 0. Let me see. Let's see what's happening here in our comparison. Info A, B. This is called the debug sigil. Everybody always asks me. It's quite nice. We actually don't need it here though because we have numbers, I think. No. What do we have here? We have references? No, we have characters. So we do need it. So that doesn't run. This needs to be ... equals. That's it. So if we do 0 ... 0, then we have no items, which means that this iterator is empty, which means that I guess all passes on an empty iterator. Let's check the docs for that. An empty iterator returns true. So that is a good thing to be aware of. By writing our range like this, we will never have an empty iterator, but that is what was happening there. And then we end up with this number, which is significantly smaller and hopefully the actual answer. Yes, that is a gold star. Cool. So the approach was fine. This does run in, I don't know. Maybe we benchmark this. The difference between a debug build and a release build is significant though. So see how the release basically happens. Well, you're not going to see that in the recording. Let me keep talking, and here's how the debug. Let me keep talking, and this is how long the debug one takes, and this is how long the release one takes. And hopefully you can see, even though those timings aren't that different, the release one is basically immediate, and the debug one takes a split second. So we actually really don't have a lot of like optimization work to do. We definitely can do optimization work. For example, maybe we do optimization work today. I think we have a little bit of time. So if we run cargo bench day 2, we can see pretty immediately, I already have these benchmarks set up. So in my repo, if you want to see how to set up a benchmark, that is in my examples. But you can see that we're doing like milliseconds worth of computation here, which is kind of slow when it comes to advent of code. We have, I think, 4 or 5 nested loops here, which is quite a lot of nested loops. There's at least one place in which we could be parallelizing and aren't. And that is right on these ranges. Do I not have rayon in here? So we're going to bring rayon in. Rayon.workspace equals true. We're going to go to part 2. This should come up now for into par iter. We do need to bring in the into parallel iterator trait from rayon. And there is clearly an issue. So let's see what the compiler has to say about that. So if we give a small rewrite here and we do ID ranges into par iter for each, that gets us into these iterators. We were writing them as for loops, and we're doing for loops with outside mutation, which now that it's parallel ends up getting captured. We could change this up a little bit and do a map and let mute total equals 0, just right inside the iteration. And for the cost of a very small rewrite, our tests are still passing, and our previously 75 millisecond runtime is now down to, pick whichever number you want. The fastest is about 13, the slowest is about 20. Median and mean are about 16, 17. So a pretty significant performance improvement for a very light refactoring. It's now running even faster than our part 1, which isn't using Rayon. So Rayon specifically is kind of really easy free performance wins, especially when it comes to advent of code problems. Now, obviously, we still have the kind of issue, so to speak, that we are looping quite a bit here. This logic could be done in better ways. This is just the first way that I came up with to solve the problem. I don't think that we actually need to allocate here. I don't think that we need to turn this into a string, but turning it into a string is definitely the approach that, for the most part, I would suggest to newer Rust developers. But there are other alternative approaches that people use for advent of code, like using ilog10, etc. I think for today, we'll leave it at this. Maybe I'll rewrite it and go over the more optimized version tomorrow morning. If you did end up using the more optimized version or you have a different implementation, leave it in the comments, and I'll see you tomorrow for the next one. Have a great rest of your day.